Hey, welcome back. In the previous video, we've talked about using PRFs to de-randomize the tree-based signature scheme, and in this way getting rid of the state also. The thing is that we've left out some of the details, and the lecture actually calls for a very specific pseudonym function to achieve this. Now this tutorial is about building this very specific pseudonym function. So if you look at what the lecture notes write, we are saying that if we use a key of length n, then this pseudonym function should have this signature. So it should be able to take as input any bit string of length at most n plus c for constant c, and it should output strings of length L of n. If you remember, a normal pseudonym function is length preserving, meaning that its signature looks like this. But now we need this more special kind. Why do we need this more special kind? Well, it may happen that the gen and sign algorithms, that they use more than n bits. So they may use polynomially many random bits in their computations, and usually they will be more than n. So our pseudonym function, which should provide randomness for these algorithms, should also output at least L of n bits, so that we can be sure that we have sufficiently many random bits for gen and sign. And then this other requirement of being able to take bit strings of length at most n plus c comes from the way that we use it in the construction. Essentially, if we're generating a key for the node called m1 through mj, that's just the name of the node in the tree, then we call the PRF using this constant keygen in the beginning, and then the name of the node. If we want to generate a key, we call this PRF with the name of the node and the prefix sign. As we've talked about before in the previous video, this is like a neat trick to make two random functions out of one random function. So this is why we need the plus c part, because these two constants here have length c. So the easiest way to achieve this is just to use c equal 1, and then just say, okay, keygen is the special symbol 0, and sign is the special symbol 1. This would work. Anyway, that's where the plus c comes from. And then this name of the node is something that is a bit string of length at most n. So we had, for example, the root node that was called epsilon. And then down here we had the whole message as a name of length n. So that's where these requirements come from. So we'll start with the easier part. How do we get this longer output size? So we know how to construct PRFs from one-way functions, or more specifically one-way permutations, but it's also possible from one-way functions for this standard format. So for output length n. Now, if we had such a function, how could we extend it to output length L of n? Any ideas? Yeah, so there are probably multiple solutions, but the easiest one, the most straightforward one, is this is a perfect job for a pseudonym generator. We have a short, admittedly pseudo-random, but mostly random looking string, and we want to have a longer pseudonym looking string. So essentially, we can just do this by applying a pseudonym generator with the appropriate expansion factor L of n to the PRF value. And that's our new PRF with output length L of n. Now you would have to formally prove this, but this is not all that difficult. So this is already possible if we have a PRF of the form that it outputs, let's say, in bits. We can always just extend this arbitrarily using a PRG. Like arbitrarily in this, like polynomial expansion, of course. The more interesting thing is this part. So how do we get the PRF to also work for like smaller inputs? Do you have an idea? You can, of course, assume that we have a PRF of the normal format already, and you can ignore this L of n for now, because we can always, like this argument that we did here, it doesn't really depend on input length or anything, it just extends the output. Okay, I'm assuming you've thought about it. There are also a lot of solutions here. The easiest that I could come up with is essentially we just replace the security parameter with this n plus c plus 1 so that we get a PRF like this. So we'll just artificially inflate the security parameter a little bit. And now what we can do is we take the following function. And in this function, we just take some x of length at most m plus c. Then we write at least 1 before the x and pad the rest with just zeros. And then we output the PRF value at that position. So then you can think about it again, like if this were a random function, that this would actually output, for example, what we would expect, right? So for example, these two inputs must produce outputs that look completely different. And this is what the PRF will do if I give it these two inputs, because they are different. Mapping this x to the padding and then the x is an injective operation between bit strings of length at most n plus c and bit strength of length n plus c plus 1. And then through this, I get the thing that I want. Okay, so putting everything together, we get this padding idea and just this inflating a little bit the security parameter, meaning that if we set up the signature scheme for security parameter n, we would actually generate a PRF key of length n plus c plus 1, but then just makes it like more secure, so this should be fine. Then we use this padding trick in order to kind of extend the domain of this function to bit strings that are also less than n plus c. And then essentially in the end, we can always just apply a PRG to extend the output size if this n plus c plus 1 is not large enough. Then one thing we have still a little bit neglected is that the definition for PRFs doesn't actually allow for like these funky forms here, like the theorem actually needs from us. So we need to generalize it a bit. So what do we need to change? So this length preserving is not a thing anymore. And essentially now we're not comparing against functions from func n anymore, because those map from n bit strings to n bit strings. But instead now we would use this function space. But then essentially the definition with these changes can be easily fulfilled by the PRF that we came up with at the top. Now we're just comparing it to a random function from the actual proper ranges. And this thing is not length preserving anymore. All right, that's already it. That's how you can get this PRF, this kind of strange looking PRF with slightly different properties. So this whole construction that we've seen before still works. So overall, as soon as we get to it, we will definitely have the statement that if one-way functions exist, then also we can construct digital signature schemes. And this PRF that we have here is definitely not getting in our way. See you.